Let us talk about distributed loads with um, shear forces. So anytime you have a load either at a point or distributed, remember that when you create a cut through your element, you can find the shear force, which is a force perpendicular to the element, and you can find that force anywhere. So we want to continuously characterize the force throughout the element. That force is, if you want to represent it in a graph, is going to be uh, like like this, where your y-axis is your shear force and your x-axis is your distance. So they're giving us distance L and 2 points A, B, where we have fixed forces in A, and AX is going to be 0 because there's no other force in X. And we have a distributed force which is going to be W times L. That is the magnitude of this distributed load. And of course, if you want to place it at a point, it's going to be at L over 2. So the three important points right here are at 0, at L, and at L over 2. So the shear force in this element will be as a function of L or X, and we can find the external forces doing summation of forces, doing the equation. We want to know what's the force at 0, at L, and at L over 2, and at any other points where we have a change in the behavior of the force. So if you have a distributed force here, then we have to find that point and draw it on the graph. So to find the forces, we can simply do AY plus BY minus WL. This is equal to 0. All right, so obviously in this case we know that we know this information. It's the load and the length, but we don't know A and B. So we have one equation and two unknowns. So if we do summation of moments at A equals to 0, and we place the load at L over 2, which we know how to do that by now, we can say that we have a positive moment at B times L minus WL times the distance, which is L over 2, which is equal to 0. So BY times L is equal to WL squared over 2. So we know that BY is equal to WL over 2, which is what we have here. And that means that AY is equal to WL minus WL over 2. So 1 minus 1/2 is 1/2. Therefore, AY is equal to WL over 2. So we have the reaction forces. Therefore, if we want to draw the graph, we know that at 0, we have a positive reaction, AY, which is W times L divided by 2. And at L, we have a positive reaction, which is WL divided by 2. So we have two options. Either we place it here, or we place it down here. In this context, positive means pointing up. Okay, so remember, you can move a force in space. You can move the vector in space, but the direction and the magnitude is what gives you the value of the force. So pointing up means positive. It's not important if it's underneath or above the x-axis in terms of the positive force. If it's underneath or above is in terms of the whole system. So where is that? We have to find the force. That's where we find, or equation of shear forces with respect to x, because these vertical forces are shear forces. And the equation is like so. So if we want to find the shear force as a function of x, we simply integrate the load with respect to x, and this is a negative load. So this is the equation right here. We have an initial force at A, and we have to find the reaction force as a function of x. This integral will give us negative wx, so this is a slope with negative, this is a negative slope, and is going to be all the way to L. So it's interesting that at L over 2, we have a shear force of 0. So this is an interesting aspect right here, because it's counterintuitive if you think about it, because the deformation, if you were to measure the deformation of this element, would be like this. The maximum deformation would be in the middle. Like you would expect this element to break near the middle or at the middle. But it's telling us that the force is 0. The shear force is 0 at L over 2. The shear force is 0 right here. And that's because we have this maximum deformation at it's a flat. If you notice here, the gradient is 0. This is a change in deformation back up. So that's why this point has a deformation of 0. So it's counterintuitive, but now that you see it on the plot, you see that the maximum shear happens at A and B, and the minimum shear happens at L over 2. And it's just basically what we're saying, because this force has to, you have to close the diagram of shear forces. All right, so the second thing is, since this is going to be a straight line, it's degree 1, the moment is going to be the integral of this slope. The integral of a slope is a parabola. It's a second degree curve. So if you integrate this again, you're going to have x squared over 2. So to find the moment, we basically have to integrate the shear force with respect to x, and that integral will give us x over 2. So if you plot a negative parabola starting from your 0 moment, your 0 point at A and B, then you can have your parabola, which is the integral of a straight line. And the maximum moment is right at L2. So interestingly, even though the shear force is 0 at that point, then but that point will give you the maximum moment. And if you notice, this is a flat tangent, a 0 tangent. So what that means is that the derivative of the moment with respect to the direction at this point is 0. So that's why you have a 0 value on your shear force. Okay, so this is the derivative of the shear force. At the maximum point, you have a 0 gradient. Remember, the 0 gradient in a derivative is basically there's a change in concavity, or a change in sign. So that's why we have it here in the shear forces. So remember, maybe you have to go and look at your calculus book and review the meaning of a derivative. But if they ask you what's the maximum value of the moment, well, in that case, you have to solve for the moment with integration. So from here, we know that the shape of our shear force is negative load times x. And when you want to find the shear force the throughout the graph as a function of x. At this point, um, is basically you have a point crossing B. So if you remember, you have ax plus b. So we have already the shape of the slope. We have the magnitude and the slope, but we don't know where it's crossing the shear axis. So in order to do that, we can find the slope with respect to b. And in that case, we can simply say, okay, my shear force is going to be VA, is the shear at A, minus the shear at any point with respect to x. So VA is WL divided by 2. We found that. So V is that magnitude right there. WL divided by 2 minus WX. Okay? So this part right here is only to find the shear as a function of x for this distributed load, because this is an area. Since this is the area, we have the magnitude W and the length is x. So the area under the curve is W dx from 0 to L or from 0 to x. So this is basically the shear force as a function of x. But we already found the point A and B. So that's why we can find the V, the shear force, as a function of x for the whole system, which is this. So if you notice, this right here is the cross at B. This is the intersect, WL divided by 2. Okay, now by integrating this, which is right here, by integrating this, we get the maximum moment. In order to find the moment, we'll have to integrate the shear force as a function of x. So let's do that right here. Moment is equal to the integral of Vx dx from 0 to L. Okay, let's see what that means. That means that integral from 0 to L of WL divided by 2 dx minus integral from 0 to L Wx dx. W is a number, that's the load, so it's a constant, therefore we can take it out. And we can say that this is the same as WL x divided by 2 minus WX squared divided by 2. This from 0 to L, from 0 to L. This is equal to WL squared divided by 2 minus WL squared divided by 2. This is 0. Yeah, it's because I'm finding the moment at this point. Okay, good. So what we need to do is do this at, right, let's fix this. So let's do a general iteration constant. So x prime and x prime. So when it's L is 0. Okay, let's do when it's L over 2. We have, when it's L over 2, we have, let's fix this. WLx over 2 at 0 L over 2 minus 4L over 2 minus W x squared all over 2. So the integration is the same. The only thing that changes is the limits. So we know that at 0 and at L, the moment is 0. The maximum would be at L over 2. So let's find that value. So that would be WL times L over 2 times, this is L over 4, minus W L over 2 squared divided by 2. This is equal to, this is L over 2 divided by 2. So this is equal to WL squared over 4 minus WL squared over 4, the whole thing divided by 2. Okay, so this is equal to WL2 over 4 minus WL2 over 8. What are they saying is the maximum? WL2 over 8. Let's see, how come I'm not getting that? L over 2. W else, this guy right here is W over 2 L 2 times L, yeah, minus W over 2 of L squared over 4. So it's 1/4 divided by, it's 1/4 minus 1/8. It's 32. Eight minus 4. This is equal to 4 over 32, which is equal to 1/8. Okay, good. So this is indeed 1/8 of WL divided by, yeah, okay. So we just have to do this subtraction. So 1/4 is 0.25. Yeah, and 1/8 is 12.5. So 0.25 minus 0.25 is 0.25. Right? So 0.25. So 1/4 minus 1/8 is 1/8. Okay. So it's not a typo. That's correct. I apologize, I didn't see that earlier. So indeed, this is correct. So the maximum moment is the change in sign for the derivative, and that maximum moment is 1/8 of the load times the length squared. All right, so from that, we can go ahead and do this example. This and that. Let's move it over here. Let's go ahead and move. Well, let's try and solve for this example. So at this point, they're not giving us any functions. They're giving us numbers. So what we have to do is draw the diagram for the shear and bending moments. Alright, so first thing we have to do is locate the points. Let's draw that a little better. Okay. And then we need to do another one for the moment. Okay, so that's x, this is v as a function of x, the shear, and this is the moment. This is going to be the first degree. This is going to be the integral of v, but we don't have any functions, we have numbers, but we still have some areas that we can compute, so it should be even easier. Okay, so the next point is B, C, and D. Okay, so B, C, D, and E, and this is A. Okay, so first things first, let's find the reactions at A and D. So we know that here we have a fixed force, AY, AX is 0, and DY. This is going to give us one equation and two unknowns. This value right here is 1.5, which is W, is 1.5 times 8. So let's do calculator. It's 1.5 times 8 equals 12. 1.5 times 8 equals 12. So this load is 12. This is kilopounds, and this is feet times 12. This is 12 kilopounds. Alright, so if we do summation of forces, we get summation of forces in y equals 0, positive that way. We have AY plus DY minus 20 kilopounds minus 12 kilopounds minus 1.5 times 12 minus 12 equals 0. So we have one equation, two unknowns. There's not much we can do there. Only we can just simplify a little. AY plus dy is equal to 20 plus 24 is 44 kilopounds. Okay, so now we can do moment at A for the second equation. This is positive up. Summation of moments at A, positive counterclockwise, equals to 0. We have that nothing happens at A, but we have a negative moment of 20 times 6. We have 20 kilopounds times 6 feet. We're going to keep it all in feet. Then we have 12 times 14 minus 12 times 14. The next one is, we have to place the force right here. So we're going to place the force at the middle and at 4. That means that this is going to be, well, first of all, is dy times 24. That's the support, plus dy times 24 minus 12 times 6 and 8 is 14, and 10 is 24, and 4 is 28. minus 12 times 28 equals to 0. Okay, so from there, we can say that dy times 24 is equal to 12 times 28, 336, plus 12 times 14, 168. This is negative or plus? 20, this is negative. So to the other side with a plus sign, 20 plus 6, which is 120. So dy is equal to 120 plus 168 plus 336, 624 kilopounds times feet, and divided by 24 feet. So that number divided by 24 is 26. Therefore, dy is equal to 26 kilopounds. Okay, that's good. So we have this value, and now we can come to find ay. So ay is equal to 44 minus 26, which is equal to 44 minus 26, 18 kilopounds. All right, that means that we have the first information to go to our graph. So let's go to, we know that there's no moment at A, so let's start from 0, but we have a force of 18 going up. Okay, so this is 18 kilopounds. Now, there's nothing else from A to B. There's no distributor load, there's no extra load, so we go straight. So at 18, and then we go down 20 kilopounds. That will put us at -2 kilopounds. All right, so from B to C, we go straight. There's no distributed load, and the next thing we see is that we're finding another load with a value of 12. So -2 and 12, that is -14. All right, let's take a pause and see what the moment looks like. So we don't have a function, but we have an area. This area is a polygon or rectangular shape, a rectangle that is 18 times 6. So 18 times 6 is 108. Okay, so we know that this is a constant. This is a uniform shear of 18. Therefore, if you integrate 18, you're going to get 18x. Okay, so the maximum value of this shear, the maximum value of the moment produced from this shear is at B as Bravo, because that's where the load is. So it's going to be increasing until you reach the maximum, and the maximum is 18 times 6, which is, we said it was 108. So the maximum from at this point, we find a maximum from the load at B, from that load of 20 kilopounds, which is 108. This 108 is 18 times 6. So instead of doing all the equations and solving for x and y and moment and shear, we can do the area. So 18 times 6 is 108, and this is kilopounds per feet. So we know that if this is uniform, then if this is a uniform load of 18, then the moment is going to be slope. It's 1 degree above. This is a constant, then this is going to be a constant times x, the slope. All right, we have our first moment drawn from A to B. Then we have from 20 to 12. Well, first of all, from 20, we said that we go down 20 and then goes straight. So this area right here is -2 times 8. So -2 times 8, this is equal to -16. So 108 minus 16 is 92. And 92 is the value of the next point. 92. And this is a uniform value. This is a uniform, this is a constant, -2. Therefore, this is going to be a slope. This is going to be a line, a straight line from from B to C. All right, at 92 kilopounds per feet. Now we have -12, and that -12 is going to be a straight line. So that puts up -14, and -14 will be straight line up into D. And at D, we went up, what is D again? D was 26. So -14 plus 26. So that is, sorry, -14 plus 26. What is going on here? Well, 26 minus 14 is 12. So it's negative. So -14 plus 26 is going to go up to +12. -14, and then we have a force going up with a magnitude of 26. So all this is 26. All this length is 26, but that will take us to a value of 12 in the shear axis. Okay, so we are -14, and we add 26, that will put us at +12. But then we don't have a straight line because we have a distributed load, and that distributed load is 12. That goes for 8 feet. So that will be like so. Okay, so let's see how much is this area. This area is 10 feet. So this is -14. Of course, the area is positive, but the values, the magnitudes are not positive. If it's negative area, means at negative magnitude. So -14 times 10 is -140. So this is -140. What that means is that 92 minus 140 is -48. So we have to go all the way here to -48. At point D. Okay, so this is going to be a line from 92 to -48. Okay. All right, that's at point D. We have it at point D. Now we have the last point, at point E. So we already know that if you notice, this is from the example before that, we have a negative slope. Therefore, the integration of that is going to be a negative parabola. So we know that a negative slope will give us a negative parabola. So let's find the area of this number right here. This is 8. Therefore, this area is 1/2 of 12 times 8. So 12 times 8 equals divided by 2, 48. Excellent. So that means that this area is 48, therefore we have to go up 48, will take us to 0. So this area right here is 48, and the shape of this curve is a negative parabola. Let me try it again. Yeah, like that. Okay, so the shear diagram is this one, going to 18, then coming down -20 to -2, then coming down another 12, so -14, and then going up this distributed force of this dy. This y was 26, which put us at 12, and then this is 12. The distributed load is 12, so at 0 is 12, coming down away from the maximum, coming down towards E. Right, this is basically a distributed load of the shear moment, or the shear force, I mean. Right, so from 12 we have to go back to 0, and that makes sense. So this is not as if we had a force of 12 here, it will be straight uniform force and then 12, but that's not what we have. We have a distributed load. That's why it is a slope. Okay, and then in the moment it's pretty easy. Instead of doing the summation of forces, you can do that, but I think it's simpler if you do this diagram approach. So this area is 18 times 6, so that will put us at 108. The max, so the value 16 times 6 is 108. So at B you just draw point at 108, and then since this is a straight line, a uniform line, horizontal, then you go 1 degree above, because this is the integral of this line would be a slope. All right, and then I didn't mean to draw that. Okay, and then you keep going with the rest of the areas. You force this area right here is -2 times 8, so that's 16, down to 92, and so on and so forth until you make sure, you have to make sure that it's closing at 0. If your shear force is 0 here, you have to close at 0, otherwise your diagram is not correct. And we got that because we found that this area right here was 48 units. So we were able to go from from -48 to +48, and the shape is a negative parabola.